In this problem, we're told to treat this compensation level depth as though the pressure there, due to the crust and the mantle above it, is completely equal everywhere at this depth. Now we want to find d, this value right here, the depth of the mountain's root into the ground. Now, since the pressure should be equal at both points A and B, going off of this compensation depth premise, we should be able to take the gauge pressures at both points as though they were equal, despite the disparities in the composition of the mountains and mantles above it. As such, let's set those pressures equal to one another with careful regard for the fact that different materials of different densities are acting above both points. And also, I've set rho c to be the density of the crust, and rho m to be the density of the mantle. So we want these two pressures equal to one another, and remember that a gauge pressure due to a depth below a surface is equal to the density of the material times the acceleration due to gravity times whatever the depth is at that point. In this particular case, however, there are different densities to work with and different heights to sum up. For the pressure at point A, we have the density of this continental material summed up along the depths of capital H, T, and D here, plus the density of this small little segment of mantle right here. So we can use this formula to find this by saying that the pressure at A will be equal to the density of the crust times G times the height at that point times the depth of the root, which is going to be capital H plus capital T plus D. And of course the total pressure is also added onto this different density for the mantle here. So let's write this as a separate term that we're adding. So plus the density of M times G times, and we'll call it Y minus D, since that gives us the height of this segment right here of the mantle. And this is going to be equal to the pressure at point B, which is a little bit simpler. It's just going to be the density of the crust times G times T, since that is the only thickness of the crust above point B. The density of the mantle times G again, times this time just Y, since Y is the distance from the crust to the compensation depth. So just Y. Now we want to find D, so let's start trying to solve for D. And let's start that by canceling some variables out first. We can get rid of G first of all, since that's in every single term. And I've also distributed out the parentheses so that we have our terms much more clearly listed out here. And this also makes it more obvious what can be canceled out, because this rho sub c times capital T cancels out with the term on the other side, since we can subtract both sides by that. We can also subtract both sides by rho sub m times lowercase y. And let's put both of these terms with the d on the other side, since we are trying to get d on its own still. Now let's factor out the d. And finally, let's divide both sides by rho m minus rho c. And this is our final formula for the depth, d, of the root. Now all that's left to do is to plug in our densities and our value for h, the height of the mountain above the ground, above the continent. And plugging those values in, actually, in this case, you don't actually have to convert the densities from grams to kilograms or centimeters to meters, because in this case, those units will actually cancel out. So it's very useful to understand dimensional analysis for bits like that. But nevertheless, if you plug in those values, then the value we get for d is 44 kilometers. And that is the depth of the root.